else. So I just want to thank Pete, Nick, Jonathan, Scott, my collaborators for the main part of this, and Amit Tel and Liz Munch for another part of this project. Hopefully I'll get to talk about both sides in some detail. My plan is this. So I'm going to recall what persistence modules are, and it's well known by now, but maybe not by everybody, that persistence has it's nicely into category theory language. So I'm going to recall, for those of you who know it, explain for those of you who don't, that we fit it to this language. And try to emphasize, you can do once the language is in place. That is not just an empty translation, but it actually helps us a little bit. So, recall. So persistence module it consists of the following data. So the selection of vector spaces T is a parameter, and also a collection of linear maps. ST from S to VT maps. I'll say this respect identities. S is always the identity, and it respects composition. So if I go from P to U, I do it in 2 steps, so I can do it in 1 step, and the same object. Right. So the key example is sub-level set, sort of original example. What you have is you have a function f, which is continuous, but it sort of doesn't seem to matter too much. Base x what we do is we consider top level set. So f inverse of minus infinity. So now a sequence of or a sort of family of topological spaces is too much. So we simplify it and we do stuff like extract the homology. Now with coefficients, that gives us a string vector spaces and give us these linear maps. And so this is a persistence module. And so somehow the structure of this persistence module is variant of the data, which is x and the function x. Now, what are things that we do with this? So we compare them. So how do you compare two persistence modules, V and W? We need is of interleaving. Interleaving is what you do is you pick an epsilon, and so you look for linear maps in 2 directions. Vt to Wt plus epsilon. And go from Wt to V of t plus epsilon. And so you have a whole family of maps one way, a whole family of maps the other way, and you have various things commute. And so most importantly, in particular, if you go from V to W and back again, then that's the same as staying in V and shifting up according to the linear maps for V. So whenever you can create this data with all of these cross maps, you say you have an interleaving. So this interleaving, there's an epsilon, and so what you can do is you can then define a distance interleaving. Which is basically the infimum of epsilon such this can be done. So I'll just put dots there. Right? So you look for such a thing. I guess you can do it with epsilon equals 0. You're saying that the two sets of data are isomorphic. They might not. So you let it slip a little, and then you look for the smallest epsilon that works, and gives you a distance, and you can show that it satisfies the triangle inequality and it has lots of good properties. Now, what's well known is that in applications we don't restrict ourselves to the persistence model itself. We do is we convert it into something called a persistence diagram, which probably all you are familiar with. I'm not going to do much about persistence diagram, but the point is that this distance, this interdistance, plays nicely with one of the natural distances that you would get a persistence diagram. So this is the starting picture. So next is I'm going to translate into a slightly more general language. I'll give a couple of examples. Having done that, I'm going to be interested in, so this may be the interesting part for me, I'm going to be interested in what comes of the notion of interleaving, comes of the notion of interleaving distance in these slightly more general settings. Point, well known, and it's both implicit and explicit in people's observations on this. So, it's the same factor from the category that I'm just going to call the real numbers, the category of vector spaces. Right? Okay, now what is this category that I'm going to call the real numbers? Real numbers is a partially ordered set. So it's a set. And so there's an object T in R. And the map or an arrow S to T when S is equal to T. Okay. There's one arrow, so it's this a thin category, whereas normally in a category, what you think of is you have different objects, vectors or groups, and think of morphisms as being functions, right? So there'll be a function from this vector space, this other vector space. So you think of that normally, and you think of there being lots of arrows, lots of morphisms, homonyms or continuous functions. So we're in this setting where we just say one morphism, and it either is there or it isn't there, and only there when S is less than or equal to T. Right? And a persistence module is exactly functor, because every object of R, let's say the object T of R, gives rise to an object of vect, the category of vector spaces, and every arrow gives to a morphism or a linear map. So morphism to VT. That's what a functor is, and it's built into the definition of a functor. The correspondence has to respect ideas and has to respect composition, and so that's exactly what we had anyway. And so this is the first indication that what we're talking about all along, even if we use that language, was a functor from this real line to vector spaces.
How does it remind you to make your width large enough?
Thank you. Yes, thank you. What we're going to do is we're going to talk. So we're going to broaden our language immediately. We're going to talk about, let's see, the set. So partially ordered set is the real line, but as we will see, there are many other partially ordered sets that we want to consider. Let's see the categories, so let's just say arbitrary categories. And what we're going to do is we're going to run with the idea that the persistence module is just functor. Okay. It's one of these things that we could just call it a functor instead of calling it a persistence module. So now we have to, the reason we might call it a persistence module is because the kinds of things we want to, so these object to are things that show up, have an established history of showing up when we do topological persistence. Right? Now, I'm going to give you 4 examples, sort of simple examples of how this comes up, and tell you why the extra generality is a little bit helpful. And after that, I want to talk about interleavings. One example is the level set module. So the way we do this is that P is the real numbers again. The starting data is a function from a real function on a topological space. And the sublevel set module is just, I'm going to call it F. From real numbers to topological spaces. Okay? And F of T is going to be F inverse of the sublevel set. So what I've done here is I've stopped one step short of taking homology, and I'm just going to call this thing, so this is now nested family of, increasing nested family of topological spaces. This iteration on the top space X. And in our language, it's also a generalized persistence module. The source category is a real line, and target category is theory of topological spaces. Level set module. And then the point is that then sublevel set persistence, it's AF, right? It's here's my real line. Here's the set module which takes me topological spaces. And what we know is from here we're very free to homology, right? And now we have a big thing. And so the point I want to make is that this allows us to generate a whole family of other objects, right? And then this HF is our classic persistence module. Let me show you another example of the same spirit. So that we get our sub-level set persistence, our sub-level set module by applying homology functor. Here's a functor we could apply. So another functor we could apply would be a merge tree. Well, the outcome would be something called the merge tree. Paper by all sorts of people actually. There's a paper by Morozov. Which closely relates to the things I want to say about the merge tree. So here what we can do is instead of applying homology, a different functor of our choice. So let's pick a functor, but the one I'm going to pick so from bottom to top. I'm going to pick the I0 functor. Okay, so it's the set of path components of a topological space. It's a topological space, and I pi 0, and it gives me a set. And you could also give that set a topology, a quotient topology, and so that's another story. Right now, let's just call it a set. Okay. So and now we have a whole different object. Let me just say again what it is. So I start with T, real, and I get F inverse of my infinity. And what I get is the set of connected components F inverse of the set. And the way you're supposed to think of this is that in team settings, functors to set. So probably finite sets and with some notion of tameness, they can be geometrically realized. And I'm going to give you a picture to show you what I mean. Geometrically realized. So what you have here, in contrast, I think, with classic persistence modules, where what you can algebraic realization of the homology sort of top-level set business. Here's the geometric realization. Let me show you what I mean. So, well, I guess it's implicit in my use of the word tree, merge tree. So, for example, if this is my function x, pants or something. So this is x. This is the function f to the real line. Methods. So then pi mod f can be, well, what you do, you swing up the set at each side. So the very bottom, before the very bottom, it's empty. Then you hit the sort of the equals of these pants. And there are two ankles, there's 2 points, and you go up. And as you go up, the number of points remains 2. At a certain point, there's just one connected component. Right? And because of this inclusion, components before relate, they map up. They both map to this one connected component. So you put this picture, right? And up you go. And so then this is merge tree. Now, of course, as you go above the top of the pair, as you go above the waist, in this case, what happens is you still have one connected component. This kind of goes up. So geometrically, and we call it the join tree or the merge tree. Typically, this is a well-known object that has existed for a long time. And the point I wanted to make is that somehow this object corresponds very closely to the degree of functors. I have to impose some sort of tameness to get a finite graph with a finite number of vertices and so on. And so that's where a certain amount of detailed work is. What's actually nice is that even in situations where the geometric realization maybe this nice way, you always have this functor, right? That's sort of one of the things. This functor always is, and even unstable situations, I would be comfortable calling it this is the merge tree functor. What's next? So now I want to talk about a very similar construction. This is Amit Patel and Liz Munch, the reap graph function construction. So here's another thing we can do, another example. P, so let X be a fixed space, and topological space to, I think we want it to be metric eventually. Let P be the fully ordered set, the set of, let's say, open subsets. Those subsets, or main subsets. For this purpose, for our purposes now, it doesn't matter too much. But suppose that a subset of X. So, example of a persistence model. So suppose Suppose we have a kind of map, or let's just say a map, from space W to space X. So let's call this map to F. So example, space and X real numbers. The same data that we had before. That's the space and the map to the real numbers. And that's what we can do. We can construct a distance module P to F again. So I say for every open set in U, the F inverse of U and logical space. Now notice that if U is contained in V, this image or this pullback or this pre-image, F inverse of U is included in F inverse of V. Okay? So what we can do is we can generate let me draw one example. I think I want to draw an example of this. So let's say now I have a topological space. I have a map F to the and I have a map F to the real line. So this particular generalized persistence module works as follows. Hint B of intervals in R. Okay. It's a partially ordered set because intervals can be contained in big intervals. And what you do is you say that what you're interested in interval, maybe you could make it open or closed or whatever intervals you want. The interval, you have a look and you see what sits above it. Right? So, are interested in, it's a little daunting. It's sometimes you be interested in too much. So rather you're going to be interested in something that's too much information, and then to find ways of making problems more manageable. So I'm really interested in, if I'm interested in studying the properties of a space and a map. So one way to reflect how this map behaves is to look at a possible interval, what topological space sits above it, and just as importantly, whenever I have two intervals that I compare, then the stuff that sits over one interval will include in the stuff that sits over another interval. Okay? And so what we get is you get a functor int to top and just as before, we're completely free to now, so let's say this is our primary object of interest. How do this pattern of topological spaces sit over the different intervals? This is a much more complicated category than the real line, although not that much more complicated, because the interval can be parameterized by a couple of points, right? So we've got this as our basic object that we care about and we want to study. We can homology, for example, convert this to a sum from int to vect. You could take height, and that would give us a function from int to a set. And so I'm going to go into the pi naught version in a minute. But the thing I really want to say is that so the work example Minor, Adels, Brunner, and Hera on extended persistence, and so work by Tomate and Dan Bergalia, and there's people since then, is that you have a theory of extended persistence, and you have a theory of interval persistence, dedicated to understanding how a space sits over the real line. And what you're really doing is you're studying this functor from int to vect, okay? Or sequence of functors, because you can take homology in any dimension you want to see it. So look at this version. So for every interval I, what we interval I, or the sort of pi naught version, the set of connected components F inverse of this all. Right. This is the work with Amit Patel and Liz Munch, because what we do is we say, so what data? Well, let's sort of see. What I want to do is I want to redraw my picture and form what is called a Reeb graph. So the from to set. The thing that I made before, and this will amplify a little bit, so the claim condition can be geometrically realized. And yet is the classic Reeb graph. And I'm going to say a few more things about what these conditions are and to sort of remind you what the Reeb graph looks like. So what the graph definition it looks like is you look at a real line and you point and you look at the slice that lives above a given point. So here's slice, this is the slice above this point, and you count the number of connected components, and then you sort of identify 2 points if they lie the same connected component, and the question will have those 2 points in this case. If I go somewhere else, this is the critical point where the two components merge into one, and a bit later they split again, and a bit later you have a zone when there's one connected component. So that is of pair WF such that fiber becomes a set of connected components, but they become an alternate fiber. Okay, now there's a gap in what I said. Because of the gap. The gap is that on one hand we have very geometric objects, and on the other hand we have functors between int and set. For merged trees earlier, it turns out that closing that gap doesn't require very much work. Like a function is, under conditions, will automatically give you a geometrically realized object. In this situation, in this Reeb graph situation, there's a specific extra thing that I need to say that this is going to work. And the extra thing I need to say is the node of cosheaves. So let's say it like this. So note. So this functor is arbitrary. Now let me try to explain to you why it's not arbitrary. So my real line, this is my space sitting above it, and let's suppose U and B. So the reason it's not arbitrary is if I am interested in pi naught F of union B, it can be determined by, if I want to know the connected components over here, I can obtain it by gluing pi of U and pi naught F of B over a common subset over the common, let's just write this, over naught F of U intersect B. Right, so might not be a subset of these two things, but Google Maps certainly give us maps for this. Okay. So I can remove this comma. And so by gluing language and category theory is that this is the same as a colimit. So it's not just that I have an arbitrary functor from int to set. It's that this functor is actually very deeply constrained. This is just one instance of how it's constrained. Is that what you can do is you can argue that actually the constraints, so the constraints equivalent already exists in theory. So the constraint, so this kind of claim that you can evaluate connected components by doing it sort of locally and patching together, the constraint is exactly the same as saying that pi naught I will say more about what a cosheave is. This is just, if you're familiar, then you're familiar. If you're not, then it's really saying that you have something that respects gluing relations in a particularly nice way. And so part of this is well-established theory of sheaves and cosheaves and so forth. And it's very familiar geometric construction. The Reeb graph, a category of Reeb graphs, or Reeb-like graphs, and there's also a category of cosheaves, and these two categories are tightly connected to each other. And that's sort of the point of view I wanted to bring across. Okay, now we have 10-ish, 15 minutes where I want to say something about inting more generally. And we've worked with partially ordered sets, partially ordered set of intervals, or the numbers. And now you may also sometimes want to work in more general. Okay. Let's say we are interested in characterize GPM, generalized persistence modules of P. Okay. So this is an interleaving. So before an interleaving was we maps that go from Vt to Wt plus epsilon, and maps that go from Wt to Vt plus epsilon. We want to be somehow coherent. So setting, suppose we have V and W to C. Now suppose V is an arbitrary partially ordered set. It's not real numbers anymore, so we can't just add epsilon. Maybe there are other things we can do that we would want to do. Let's define two closed maps. From E, gamma, and kappa. So respect the process structure. So gamma of x is less than gamma of y, x is less than y, and ditto for kappa. I'm going to assume that x is always less than gamma of x. Okay. Which says, when I compare V with W, I look ideally if there are more things just go horizontally, but if I can't, I go up a little bit. And the point is T plus epsilon is up a little bit. And so that's what this second condition is. So these things together say that gamma is a triangle. And now, the idea is that an interleaving is the following thing. So for every V of x, so before it was V of t, now the general process is V of x. I have to find a map from x to gamma of x. And so maps. I find lots of maps from W of x to her. And I guess what I want is then so let's say maybe one set of maps is called phi, and the other set of maps is called psi. So maybe what I also want is when I do phi and then psi, I get back to the internal map for V. This kind of data is I would call. So this would be a gamma is a translation. It's a way of shifting up a part of the set and kind of then tells us that V and W, the distance modules V and W, are interleaved with respect to gamma and kappa, right? Or we didn't have to say with respect to gamma and kappa. We could say epsilon is one epsilon. Here we will be, there's different possible translations. Okay. I hear the story. So the story is there's two. So the thing I want to say about part one is two by putting two there. Maybe too much here. There is something, so we introduce an idea called a span. Okay. And I can actually do this for arbitrary categories, not closed sets. I'm just showing you do this real line as a closed set, and the rest will be by suggestion. So suppose I have, I'll just do it first in an arbitrary process. So suppose I have gamma kappa like this. So the cospan is really I of gamma kappa is the following thing. It's P cross 0, 1. There's 2 of P. This P is a copy of P. Within each copy, so then I would say 0 is going to be equal to x 0 is going to be equal to y, is going to be equal to y1 if n is less than or equal to y. And interesting ones are, if crossover, I compare things, but I have to move up by gamma, right? So then I can say x0 is less than or equal to y1 if gamma x is less than or equal to y. And similarly, is less than or equal to y0 if kappa x is less than or equal to y. So here's, we have this way we create 2 shifts. These are going to allow us to compare 2 persistence modules, but with a little bit of flexibility accorded to us by shift. And now what we're going to do is we're going to convert this into a much bigger partially ordered set. So there are 2 copies of P. Each slice, the partial order is the same, and to go across, I need to go up by at least gamma before I can start comparing things. Right? So that's okay. I'm going to actually read it as 2. So that's the notion of a cospan. And so the first conclusion I want to write is that things so if I have V value of exactly the same thing as saying function so what's the function diagram? So I have my copy of P. I use it as the left term of it by gamma kappa. The right term of kappa. And now I have my first persistence module V and second persistence module W. And so the point is that is an interleaving if I a functor from this combined category to target. Okay, so that's really what interleaving is. Interleaving is W are closely related if I can find a suitable span, we call this, such that these 2 modules separately are part of some bigger module. Now, what I like about this formalism is that we don't really need to restrict to partially ordered sets. We can let P, and they don't even have to be the same. We could have a category P, another category Q. We're interested in comparing some third category, and so you can do this is you can say, okay, so what's the cospan of 2 categories? It's a larger category whose objects of P joint union the objects of Q, right? And we also require that the morphisms within P and morphisms within Q are the same as they were before making the cosine. And the flexibility we have is in the cross maps. And so we have a lot of them in which we're very tight interleaving, or there are not many of them, and you might have to move a long way to find any maps at all, in which case it wouldn't be such a close interleaving. So minutes, I'd like to say something. Is anyone actually still there? Because I'm not sure if the computer sort of slightly went to sleep. Can someone shout? Hello. Thank you. Very good. Thank you. So let me do this sort of my final thought. Idea of finding GM. We must take this in partially ordered sets. So let P be a partially ordered set. So let O set. Now the idea is let trans P the translations on or the letters on P. Maps from P to P that respects the partial order, and also any x, the thing it goes to has to be bigger than x. Okay, so that's what we want translation to be. And it's to compare E from some category and W from some category. We seek such V and W are into we seek. Now, one of the things that in the classic method, the only translations we were particularly concerned with was the real line shifted up by epsilon. Not easy to measure because you shift up by epsilon, you get that that's an epsilon. Here it's kind of much more out of control. Like if you think about it, you could say even V and W, you consider the set of all pairs gamma kappa such that, and this will be a subset of P, which potentially is a gigantic partially ordered. So this is a gigantic partially ordered set, and here there's some subset of pairs gamma kappa that allowed V and W to be interleaved. And so if you make gamma and kappa very close to the identity, to translate translation, you can say that V and W are very close symmetrically. And you can't, then you don't get to say that. So my final is so it turns out that data is define a metric on the persistence module, a metric that satisfies the triangle inequality. And it's kind of very nice what we need. So we either need one of these two things. We either need superlinear function, superlinear family from the partially ordered set 0 to infinity, let me call this capital omega, to trans P. We call a sublinear projection. The dual concept, so this is a map from trans P omega to 0 infinity. Infinity might happen, so I'll make that close. The idea is, it's sort of one of two ideas. So the first idea is, so you're looking for pairs of translations that allow you to compare them. And so what you do is, rather than looking at arbitrary translations, you use a preferred family, like one parameter family of translations. For the real line, it's very straightforward normally. One parameter family is shift up by epsilon, and then whatever epsilon is, that's the family of shifts. What you need is you need that function which is to algebraic process, whatever you want to call them. You need that function to be superlinear. Like if I shift by epsilon and I shift another delta, then I want to be able to say something about the corresponding translation. There's also dual formalism, which is you every possible translation. Then what you want is you want a function omega which measures the displacement of a translation. So, for example, and then what you can do is you can say, well, what's the smallest omega of my pair gamma kappa that will give me an interleaving? That will be a metric, and the condition for the triangle inequality to hold is sublinearity. So we finished with one specific example of this. Is equal to subsets of a metric X over epsilon, and that takes a subset and replaces it with a thickening. Okay, brackets don't match. Epsilon, right? So the metric space thickening of the subject, all points that lie within epsilon of the original set. Okay. You can show quite easily that if you thicken and you thicken again, the resulting thing is contained in the. If you just thicken all in one go, it might not be equal to, but it's contained in it. And so that makes this family, in our language, a superlinear family. And so then you can use this to use this so metric, the category of persistence modules from P to the top. Construct such a persistence module. This is what we looked at before briefly. So W to X from P to top is that takes an open set and returns F inverse of U. And what's really nice about this, I haven't said too much about how these metrics really work, but you very easily get the following kind of theorem, which is if, for example, X is also a metric space,
F3 I the infinity distance between F and G is epsilon, or just anything. It doesn't have to be small epsilon. It follows that the persistence modules, capital F and capital G, have distance less than epsilon.
So this is actually the right formal properties for studying. We've spent time thinking about space maps to the real line, and then generally you can study spaces and maps to some other target space. You get a category of those things, and you get a category of distance modules that look like this, and compare them with this transition, Lipschitz transition, with respect to the metric. Stop now. But maybe I can bring it up for a question or two.
Right. That was one more math. Yeah. Do
you have anything to add, or should I run off to my midterm?
Question. Is anyone? Hi.
your computer though.
Am I muted?
Yeah.
If I'm saying things, you can hear me or not.
I can hear you.
Oh, okay. So just quick question. You mentioned at the part one where you said that when you are talking about co-span, you can assume the set no longer be a co-set. It makes me wonder, if you no longer have this partial order among the elements, how can you possibly define the translation?
Well, so I think the implicit question, how do you measure a translation? Like for us, it's very clear, you shift up and you're shifting in a particular direction, and because you're shifting in a particular direction, it makes sense to feel that you can that you've shifted, right? So your question is really it raises a sharp point, which is that you can absolutely do all of this for arbitrary categories and look at class of all possible closed spans. It turns out you have to be a metric based on, which will allow you to interleave them. That's clean and straightforward. I think maybe Peter and Jonathan know more about it than I do. They did some work recently I haven't had a chance to think about. But you're absolutely right. When you lose this sense of partial order, and therefore it becomes much less clear what you mean by translations and what you mean by how close to translations are. I will say cospan, a pair of translations will give you a cospan, but generally cospans exist are not representable by pairs of functors. And so I think that generality is quite fruitful. And again, the question of finding a good metric is something we're in the process of working out. Maybe it has no good answer. Okay, thank you very much. I'm going to run because I have some students worried about their midterm, and so I think they want to see me there. So goodbye. Thank you. See you later.
Function H.